In the last video, we introduced the idea of Einstein's happiest thought, as he termed it, and the equivalence principle that an accelerated frame of reference is equivalent to a gravitational field, and therefore you can do analyses of accelerated frames of reference and apply the results to the situation of a gravitational field. And we did that in a simple case to show gravitational time dilation, that clocks lower down in a gravitational field will actually run slower than clocks higher up in a gravitational field. And we mentioned the example of the GPS, Global Positioning System. In fact, actually, one slight correction here, I wrote down the wrong numbers. We talked about how the clocks on the satellites run slower due to special relativistic effects because they're going at a high velocity compared to the clocks on Earth. And so the difference there is about 7 microseconds. They run slower compared to an identical clock on Earth. But then you have the gravitational time dilation effect, so the clocks on the satellites higher up in the Earth's gravitational field will actually run faster. And I wrote down 43 microseconds. It's actually 45 microseconds if you want to be a little more precise about it. The conclusion was the same, however, that it was a correction factor of, in this case, actually 38 microseconds that need to be built into the system. In other words, they made the clocks of the satellites run slower by 38 microseconds a day than the clocks on the ground, just to make the whole system work correctly. So that's where we were with the equivalence principle. I wanted to do one more example with it, because it comes directly into the history of Einstein, as we'll see. And you may remember if you read the profile of the young Einstein at the end, we talked a little bit about this. But it's the bending of light by gravity. So again, the equivalence principle says if we analyze something in an accelerated frame of reference, then the results should apply, so we've done things correctly, to the situation of a gravitational field. So here's the idea. We're going to do two perspectives on an elevator. The elevator operator perspective, sort of looking from the outside, and then the perspective of an elevator passenger inside. So maybe we'll have A for Alice here. So Alice will be so here's Alice. She'll be the elevator operator, and we'll put Bob in the elevator here. I won't draw him in yet because we need to do something over there. Don't want to mess that up too much. So here's the situation. Alice is the elevator operator. She's going to accelerate the elevator upwards, either via a crane or just the regular elevator mechanism. And also, there's a little hole you can see on the left side of the elevator. We're going to insert a beam of light, shine a beam of light there. So here comes the little beam of light going in there. Roughly sort of a messy beam, but there it comes in. So remember, this is Alice's perspective. And so she's going to insert that beam of light. It's going to travel just straight across, as far as she's concerned, horizontally, as the elevator, of course, is accelerating upward. The elevator is being raised here. So what does Alice see? We've got 3 snapshots, 1, 2, and 3. So in the first snapshot, she sees the pulse of light enter the elevator. In the second snapshot, a little bit later, the pulse of light, of course, is traveling across here. So here's the second snapshot. It's going to be at the same height, comparatively. So now the pulse of light is right about there. Let's move it up just slightly here. I made something like that. So I think that's pretty horizontal there. So again, compared to Alice, pulse of light is going across horizontally as the elevator is moving up. And then finally, in the third snapshot here, the pulse of light gets across to the other side and impacts right there on the wall of the elevator down low. Okay? So that's Alice's observation, the elevator operator perspective of just that pulse of light going through a hole in the elevator, hitting the other side. But of course, the elevator is accelerating upward, and therefore it's going to hit down there. Now, what about the passenger perspective? Say Bob inside here. Well, of course, he will see the light come in, and I didn't really say this is down here. It really doesn't matter. Bob, as far as he's concerned, remember, he's not moving. Okay? Elevator is accelerating upward, but as far as he's concerned, it could just be a gravitational field. He could be just sitting on the Earth in the elevator feeling the force of gravity, or he could actually be accelerating. But what is he going to see in terms of the light beam going across there? Well, they both have to agree that the light beam comes in the hole. like that. So they're both going to see that. They can both take a little quick photograph there. They also both have to agree that the light beam hits down here at the bottom. Maybe it makes a little hole or something. There's a little burn mark, perhaps, if it's a laser beam. So they have to agree that. In snapshot number 3, they both have to agree this is where the light beam hits, right there. And in the middle picture, they both have to agree, if they could take a snapshot there, the light beam's sort of halfway from the top and the bottom. So something like this. And so look at the path of the light beam from the perspective of Bob, the elevator passenger here. Now, as we've drawn it, you could say maybe it just goes, straight down in a diagonal line. In actual fact, because the elevator is accelerating here, the effect sort of gets amplified as it's getting closer to the bottom there. And so the actual path will be a curved path, not just a straight line path. It'll go down something like that and hit there. In other words, if we took multiple snapshots here, a video of it, we'd see the path of the light from the perspective of Bob inside the elevator. The passenger would follow a curved path and hit on the wall there, whereas outside to Alice, the elevator operator, would just be going straight across, but hitting right there. So this is a very simple analysis, nothing very profound about it. It's just the elevator is accelerating. That's all that's going on here. It doesn't even have to be a very fast acceleration. So no special theory of relativity effects here. But the conclusion is, if the equivalence principle is true, that this is the analysis of an accelerated frame of reference. Therefore, this also applies to a gravitational field. And what that means is, in a gravitational field, that light will bend. Because we know, from the perspective of the elevator passenger, light definitely travels a curved path from their perspective. But again, as far as they're concerned, they could just be the elevator could be on the surface of the Earth, not moving at all. They could just feel that gravitational field. So they don't know whether they're feeling acceleration upward or whether they're stationary on the surface of the Earth and feeling just a gravitational field. In either case, they'll have to see light bend, follow a curved path. So in the presence of a sufficient gravitational field, light will bend. Actually, I should say, in the presence of any gravitational field, light will bend, but gravitational field on the surface of the Earth is not really strong enough to get much effect here. If you actually analyze, as light goes across, very quickly, of course, from one side to the other of an elevator on the surface of the Earth, the bending of light during that very short time period will be about less than half the nucleus of an atom in terms of the amount of bending it goes through. So essentially, we'll see it just go straight across. But, and here's where it comes into play in terms of the history of the development of the general theory of relativity, which Einstein put the finishing touches on in 1915. And one of the results of that was the prediction that light would be bent under the influence of gravity. And it would require a fairly strong gravitational field. Turns out, if you look at starlight coming past the sun, okay, so we can observe a star out there just past the edge of the sun, that light as it travels near the sun should be bent and reach us compared to if the sun wasn't there. Now, unfortunately, when the sun is out, obviously, we can't see the stars right next to the sun. But during a total eclipse, we can. And therefore, we can observe stars when the sun is away from them. At night, different sun's gone, of course, on the other side of the Earth. So we observe a star, and then during an eclipse, if the sun is right next to that star, the light from that star should be bent when it reaches us. And so the observed position of the star should shift slightly compared to when the sun is there or the sun isn't there. And again, we can't observe that bending unless we have a total eclipse right at that instant to block out the light of the sun so we can actually see the stars. And so they had the idea to do these observations during an eclipse to see if light would actually bend a certain amount. In fact, the Newtonian theory of gravity also predicted a certain bending of light in that situation, but a different result than Einstein's theory did. You may remember about this time, 1914, 1915, World War I was going on in Europe. So what happened was early attempts, right about 1914, failed because of the outbreak of the war. But by the time the war ended, essentially 1917, 1918, there was another eclipse coming up in 1919 that was going to be able to be observed as a total eclipse partly on the coast of Africa and across the Atlantic Ocean, and also partly in Brazil. And so the British mounted an expedition led by Arthur Eddington to see if this was actually true. So they sent one team to Brazil, they sent another team to the west coast of Africa. Unfortunately, the observations were pushing the limits of the portable equipment they were able to, because they actually had to go, of course, where the eclipse was. They couldn't just use a really nice observatory. Pushing the limits of the equipment they had, plus anytime you have an eclipse, there's also the danger of a cloudy day or whatever. And so they were up against some of that, but they did get enough data such that late in 1919, they the British announced that Einstein's theory was confirmed in this case. And it just caused a sensation, because here was a world that very weary of war and the nationalistic fervor that presaged that and built up during the war. And so here was this British expedition confirming the work of a German scientist, okay, an enemy scientist to many people, overturning the work of Britain's greatest scientist, or maybe even the world's greatest scientist, Isaac Newton, up to that point. And the press caught wind of this a little bit, and it even came across the Atlantic to the United States. And the New York Times, after this meeting of the Royal Society of London, where it was announced, had these headlines. The first headline said, "Lights all askew in the heavens." In other words, things were a little weird there in the heavens. And then they had 5 sub-headlines in the style of the day. "Men of science more or less agog over results of eclipse observations. Einstein theory triumphs. Stars not where they seemed or were calculated to be, but nobody need worry. A book for 12 wise men. No more in all the world could comprehend it," said Einstein when his daring publishers accepted it. Now, most of that was just fiction. Okay, there were more than 12 wise men who could understand it, and there were no daring publishers involved, and so on and so forth. But men of science, and they were mainly men, were more or less agog over results of the eclipse observations that confirmed Einstein's general theory of relativity and the bending of light. It was still controversial, and in fact, even by this time, Einstein was recognized within the scientific world. And then after this, the eclipse expedition that confirmed his theory, this is when he became world famous and a scientific icon. He made a tour of the United States, was invited to tour to raise money for the campaign to develop a Jewish homeland in Palestine. And so he did that. And it was like, well, later on in the decade, Charles Lindbergh, the ticker tape parades, and even later on, years later, rock stars and astronauts and so on and so forth. So he became a celebrity at that point in the 1920s. He wasn't yet the scientific icon with the white, hair going all over the place and sort of the sad, wise expression, the sage-like expression. But he certainly was fast with a quip, and journalists loved him. And so from that point on, they were often calling him up to get his latest opinions on this, that, or the other, not only for scientific matters. So that's when he became world famous. And you may ask, well, what about the Nobel Prize? He actually had not won it at this point yet, which was causing some problems for the Nobel Prize Committee, who was making these decisions. The Nobel Prize at that time really was focused more on experimental results and discoveries, and the committee was dominated by experimentalists, and people still had some doubts about the special theory of relativity and certainly the general theory of relativity. Even though the eclipse expedition confirmed the results, you could still question about the experimental analysis and reducing the data and the observations and so on and so forth. So it was fairly controversial. Einstein had been nominated for the Nobel Prize starting in 1910 and then almost every year after that. And then finally, in 1921 and 22, they had no physics prize awarded in 1921. And then in 1922, Einstein was world famous. People were wondering why the greatest scientist since Newton hadn't won the Nobel Prize yet. They actually ended up giving it to him for his discovery of the law of the photoelectric effect, one of his other 1905 miracle year papers where you may remember he had the heuristic idea of treating light as a particle, essentially, and analyzing the photoelectric effect and some other things along with that. So they were able to do that, gave him the 1921 prize. Actually, in 1922, at the same time, they gave the 1922 prize to Niels Bohr, who was a pioneer in quantum mechanics and had built some of his quantum mechanical theories based on Einstein's work. So it was a nice way to solve that problem. But what's interesting is that in the prize citation, the Nobel Committee specifically accepted, not accepted as in AC, so not this type of accepted, so not that, but accepted the theory of relativity, whether the special theory or the general theory of relativity, from the prize. The idea perhaps was that maybe he'd get another one down the line when the theory of relativity, whether special or general, was a little more accepted, this type of accepted, and also perhaps confirmed a little bit more. All of that never happened. So he won the Nobel Prize, the 1921 Nobel Prize in Physics, specifically for the discovery of the law of the photoelectric effect, as the prize committee termed it, and also it said for his general services to theoretical physics. So you could include certainly his relativistic work in there as well.